So besides the gravity, which we have here in this setup, so this is just a simple setup where gravity pulls the points down, but we will not use the gravity for this one, so we have nothing that moves our points. The first force besides gravity we look at actually is called pop force. And unlike gravity, you actually connect it up here, not down here. If you try that, it will not work. Now, why is that? The reason is that the gravity technically works with every simulation, including smoke and cloth and fluids. And historically, the particle forces only work with particles. Now, this has changed though, because basically every simulation nowadays, except smoke, so pyro, is based on points. So the particle forces that we will look at in the next couple of videos all work with all the simulations, and we will use them with all the simulations. But this is where it comes from. This is why you connect it up here and not down here, because it used to be only for particles, but this is not the case anymore. And this is probably the most important node I use when it comes to forces, because it entails two things. The first thing is just a uniform direction, and this is right here the first thing under force. And this just literally means we accelerate our points into a certain direction. So let's say positive x, which is this direction. You can't see it because my head is in the way, but let's put it to 3, 0, 0, which means this direction. And if I press start, you can see our points accelerate. And that's important because it's a force, it accelerates. That's really just a uniform direction, as you can see. And that means we can actually, if we want, use the pop force to build our own gravity force, which means we just accelerate in negative 9.81 meter per seconds, because this is what actually the force here means. This is meter per seconds acceleration. So if I set it to minus 9.81, I literally have a gravity which is basically identical to the gravity, because what's on by default is that just like the gravity, it ignores the mass. We can turn it off, but I never do this because there is no point. So by default, it does the same. That's not really that interesting, but if we want, we can do this. But as you can see, if we wanted to create some kind of wind in a certain direction, we can just give it a certain direction in the force. But when we look at it, that doesn't really feel like wind. It's way too perfect, like a perfect stream of wind in one direction, and not a single point moves anywhere else. And this is where the main reason comes in why I love pop force, and that is the next one, the noise tab. Because by default, it has a noise built in, which has an amplitude of 0. With other words, it's turned off, but I can activate it by let it set to amplitude of 1. And then you can see what actually this node is for, and this is noise. So we can add noise to the uniform direction we set up here. Now it feels much more like wind, because wind is not just uniform, but it has a bit of noise in it. Now the thing is, you don't have to combine that with a uniform direction. We can set it back to 0, and we can just use the noise by itself. And when you look at it, this is actually a curl noise. And you can see that when you look at the behavior, you can see it a little bit. This creates kind of waves almost. So it's not completely random, but it has a pattern, a wave pattern. And that it is a curl noise, I can actually prove to you, because as you can see on the little lock here, this pop force node is actually an asset. That means we shouldn't do this very often, but we can go in. And if we look into what's going on here, we actually find that the core node of this is actually a curl noise. So internally, it uses the curl noise that we've already learned in the basics. And this is important to understand because just like in the curl noise, we have a swirl size. So if we increase the swirl size, our wave basically gets bigger, and you can see that here. And you can already see why this is so important, because it instantly makes everything way more interesting. Now, as you can see, you have the strength, which is the amplitude. So if I increase the amplitude, the noise becomes stronger, or the points get faster. Then you have the swirl size, which is the size of the waves. But what you can also see is that it's actually changing. So it's not always the same direction, but it's constantly going, it's changing. And this is the pulse length. And the pulse length says how quickly basically one wave is changing. And by default it's set to 1, which means it takes exactly 1 second to do one full turn. Now, what does that mean? It really just means the lower this number, the faster it changes. And the best way of visualizing this is actually there is a built-in way of visualizing visualizing our curl noise, and that is up here under guide, and then it shows you in form of some curves what our noise is doing. And if I press start, you can see that it's constantly changing. Now, as you can see, unfortunately, it's not really helpful to kind of visualize what the noise is doing. At least that's what I feel. It's not really giving me any idea about how the behavior, those red lines. But what it does give me is a better understanding of how quickly it changes. And let me decrease now the post length, and that means that a full change in the wave takes 0.2 seconds. And this means it's just much faster, as you can see, and therefore feels more chaotic, basically. If we want the whole thing to be slower, of course, we increase the post length. So when I set it to 3, for example, and you can see now this is much slower, and you will actually see that in the behavior as well. So let's turn the guide off for now, and let's have a look again at the speed of the post length of 3 in our points. And here you can kind of see that it's much slower now than it was before. And let's try it again with 0.2, for example. And now it should be much more chaotic. You can almost see how it changes almost erratically. And when I increase the or decrease the swirl size, you will see that there's now much more chaos with a shorter post length. So those, in my opinion, are the 3 most important settings. The amplitude is the strength, the swirl size is the size of the curls, and the post length is the speed the curls are changing with. So if you want them to be really slow, you can increase the post length to something like 100, and then you will see here that the shape, well, let's increase the swirl size to 3 maybe, then you can see that the shape is not changing really, it stays intact, which is not necessarily what you want, but you can see that you can actually change so slowly that we can't see the difference. Now, usually what you do, of course, is you combine this with something, and we will see later on, basically every simulation will have a pop force in it, because whatever you do, and we saw that by just using the uniform scale, and let's bring all this back to something it was before, if you use the built-in uniform direction, by itself, it's very boring, but as soon as you add noise to it, it becomes interesting, and this exactly is the logic of the pop force. And this is why it will be always used in combination with all the other forces. So as you can see, the pop force is a really important force because it adds turbulence or chaos to our simulation, and it has a built-in uniform direction, which is often not what I use it for, but I use it for the noise alone. And we have the strength, which is the amplitude of the underlying curl noise. We have the swirl size, which is the size of the waves of the curl noise. And we then have the post length, which is the speed in which our curl noise is changing. And with this, you can usually create all kinds of really cool shapes, something like this, for example, which in my opinion already looks interesting simply because it has turbulence in it. So I hope this is helpful. In the next video, we will look at the sibling of the pop force, which is also very important, and that is the pop wind. So thanks very much and see you later. Cheers.